Hello everyone, welcome back to the cutting edge stage at Cognition X. I hope you've been enjoying the day, seeing lots of different talks, going and chatting to some fellow attendees and possibly speakers in some of the networking sessions, and of course visiting the expo. We're here for this next session, but of course there's still plenty of time today to do all of that and continue the conversation online using the hashtags on Twitter and all these sorts of places. But for now, we're here for the next session. This one's called From Making a Prediction to Making a Decision, Why Causality Matters. I'm excited for this session. Looks like we've got two amazing speakers and a brilliant moderator, speaking of whom it's Libby Kinsey again, who you guys will probably already be familiar with from previous sessions here on the cutting edge stage. So with that, I'll pass over to Libby. Enjoy the show.
Hello, thank you so much for joining us on the cutting edge stage. My name is Libby Kinsey. I am an independent researcher and consultant, and I'm a technologist in AI and machine learning at Digital Catapult here in the UK. This session is about research frontiers. We like to do some sessions on research frontiers on the cutting edge stage, and in particular, it's about causality in machine learning. In a recent paper by Bernard Scholkopf in 2019 called Causality for Machine Learning, he wrote that the hard open problems of machine learning and AI are intrinsically related to causality. And that's why we wanted to take a look at it here. We've got two keynote speakers, Rosemary and Carla. They're both experts on causal learning, but their routes to it and their domains of research differ. So it'd be really interesting to get their two perspectives. And when they've given their presentations, we're going to delve a bit further into why causality matters and what needs to happen to integrate causality with machine learning. Let's get started. First up, we have Carla Diaz-Ordaz. She is Associate Professor of Biostatistics at the London School of Hygiene and Tropical Medicine. And her research focus is causal machine learning in health. Over to you, Carla.
Thank you, Libby. Nice. So hopefully you can see my slides. There we go. So there we go. So the topic of this talk, of my first sort of provocation, let's say, is so why causality matters. So I see this as a kind of like a two-way street. So I came, as Libby suggested, I come from the statistical causal inference academic world where we know that causality matters. But perhaps what we have traditionally ignored was the use of data-driven algorithms that could help us go beyond our linear regression, for example. So my first foray into machine learning was how could I use machine learning to sort of like harness the information that was hidden in my data to make data-driven causal decision support a reality. And that's what most of this talk is going to be about. And I'm going to touch towards the end a little bit of why machine learning needs causal inference to help make the learning that we get from our algorithms more robust in the sense of tackling the lack of generalizability that we tend to see in our prediction models. So what this talk is not about is about methods for learning causal structure from the data, because I come from the traditional school of thought that correlation is not causation. But this is also a little bit of a provocation, perhaps, for Rosemary's talk. Right. So I want to give better decision support tools for sort of like scientists that consult with us as to how can we use our data to take better decisions. So what we have traditionally done in the machine learning world is to apply my best algorithm and then convert data inputs into predictions. So perhaps for a new observation for my next customer, I want to predict their purchases. And in my background, I work in public health. So perhaps it's more common to think of, for the next patient, what should be the medical treatment that I decide for this next person. But I want to start this talk by asking us, but is that really what we want? So there's been a recent discussion in the world of data science about the different goals that we have as data scientists. Professor Miguel Hernan from the Public Health School in Harvard recently wrote in 2019 a paper where he roughly says that goals are divided into descriptions, sort of like correlations between the data, features, prediction, and counterfactual, so what we're going to call causality. And this roughly sort of is equivalent to Yehuda Perl's ladder of causality, where he says the lower rung of questions we can ask and answer from data is association, again, correlation between our features. Intervention, what happens if I take an action right now, what would be my outcome, which is already a causal question. And counterfactual, which in Yehuda Perl's world is kind of something that contrary to fact, perhaps saying what would have been my salary now have I been born a man, for example, right? So I say that whatever we do as data scientists, we need to understand the aim that we are trying to achieve and then select our analysis and our algorithms which are best aligned to that goal. So let's start with a little example, sort of like a toy example, somewhat inspired by the COVID-19 crisis. So let's say that I have patient data from pneumonia patients that present at hospital for admission. And then we have lots of characteristics measured from them. So their age, weight, dietary habits, whether they have other heart conditions, asthma, lots of things. As rich a set of covariates as you want. And then my clinician collaborators ask questions. So perhaps they want to know, what is the risk of 30-day mortality for these patients? This would be a prediction model. But maybe more importantly, they also want to know, what would be the risk of mortality if I were to admit them to the ICU? Or perhaps, should I give ventilation to any one individual? So you can see that these three questions are very different in flavor. And I'm going to convince you that the last two are causal questions and that simple prediction algorithms are not going to be adequate to give the clinician the tools they need to help them decide what's the best course of action for the next patient. And choosing treatments requires both causal thinking and prediction. So let's continue with this little example. So just to introduce the concepts of causality, imagine that I have this one patient who is age 74, male, and I have all their characteristics there. And then I want to know, if I admit them to the ICU, which I'm going to denote here by A, your treatment is equal to 1, what's going to happen with your outcome, right? What would be your outcome if I admit you to the ICU? And in this example, I'm saying that your potential outcome, which is denoted by a super index 1, is this person is going to be healthy and discharged from hospital at 30 days. Now, what would have been the outcome if instead of admitted to the ICU, he's given treatment 0, so not admitted to the ICU. And in this example, I've decided that this person is still going to be sick and hospitalized. Now, this is all the ingredients I need to do causal inference, because what I want is the contrast between these two potential outcomes, and that would be the treatment effect of getting admitted to the ICU. Unfortunately, we only get to observe one of these outcomes, because for any given person, I either admit them or not admit them to the ICU, and these decisions are not taken at random. So the treating clinician decides, given their knowledge and your characteristics, what to do. So in the real world, where I don't have all this perfect information, what do I do? And this is why the causal inference literature has developed a set of assumptions that are at least sufficient to be able to make progress with observed data. So, so the ground truth will remain unknown. I'm never going to be able to observe both of these potential outcomes. So I have all your characteristics. They're simultaneously associated with your outcome, whether you're healthy or not healthy, and also whether you end up getting the treatment or not. And so if I want to estimate the causal effect of this treatment, I'm going to need to make assumptions to make progress. And, I don't want to get too technical, but we can just quickly say what these assumptions are. And so I think if I measure enough characteristics of these patients so that I can imagine that there is no extra association between the treatment that you get and your potential outcomes, given all these characteristics I'm adjusting for, which is known as conditional exchangeability, then I can use data from the people that did get the treatment to sort of like estimate your potential outcome. This means that also the treated and the untreated must be similar in the sense of having roughly probabilities that are getting any treatment, so either getting the treatment or not getting the treatment. And under these technical conditions, I can actually use data to estimate this causal quantity at what would have been your predicted outcome have I taken this action. And so I can use this to formulate a type of treatment effect that is not your individual treatment effect, because that was impossible, but a conditional average treatment effect, where I'm kind of using people that are like you in terms of those measured characteristics L. So now this can be used to decide a policy or a treatment recommendation. So roughly, if this quantity here is, for example, positive, I can say, oh, okay, so the treatment has a positive effect on this patient, and therefore I'm going to treat. Or I could say, well, I want it to be sufficiently bigger than 0 because maybe it has some side effects, right? If it is something like aggressive ventilation, and I can put this lambda parameter to sort of make sure that the benefit really offsets perhaps the adverse effects of the treatment. And also, in statistics, usually we want to know that this effect is really there, and it's not just sort of like by chance findings. So we usually would have a measure of uncertainty around these numbers, and I would want that the whole of the plausible values of my average treatment effect are way above the threshold before I recommend my system to recommend the treatment. So that's your sort of causal inference in a quick whirlwind. So where does machine learning enters in my world? So this has been all traditional causal inference. So now, up until recently, people have been using just simple models to estimate these conditional expectations. But more recently, we have been using sort of machine learning algorithms. And here is two caveats that where the two worlds collide, right? So the one naive implementation of machine learning methods would be to just sort of use my favorite predictive model for predicting the outcomes given treatment and the characteristics, and just plug it into this estimator. But it turns out that this actually results in large approximation bias, partly as a result of the tuning in process, and is much more damaging in small samples. But it's also quite difficult to calculate the uncertainty around these numbers. And as I say, if I want to recommend the clinician a system that they can trust, it is important that we understand the uncertainty around these estimators. So without wanting to give you too much detail, the way in which machine learning algorithms are brought into the causal inference world is important. So if I just want to use them for prediction, then I'm quite happy with just using, say, the machine learning algorithm directly. And perhaps I can do a smart tweak, which is to optimize my algorithm to minimize the mean square error, as opposed to just the raw outcome. But for decision making, it's important that I do it in a clever way. And for this, statistical asymptotic theory, funnily enough, is important. But that's like a topic for a different conversation. So I just wanted to quickly show you a little example of how ignoring causality can go really wrong. So this is an old example. Some people use a machine learning predictive model for mortality. And they were going to use this to triage, to decide whether to admit patients to the ICU, to the intensive care unit. So when they deployed their predictive model, they found that asthma patients with pneumonia seemed to be less likely to die, which kind of started the bells ringing, right? Because this is sort of dangerous, and kind of it went against what was expected. And so what went wrong there is that the model should have been a causal model, and they should have set it up as in what would have been the risk of mortality if the patient were or were not admitted to the ICU, and they didn't do this. And the things went even worse in a way, because in the training data, the treated and the untreated were not similar. So in particular, it was found that in the training data, there was a sort of policy that most asthmatics were immediately transferred to the ICU. But because the ICU wasn't in the model, it appeared as if the asthmatics were sort of getting healthier, right? So this has been now noted in the literature. And so if you have this type of covariance shift between your training and your deployment set, causality is actually more difficult to achieve, and we have to pay attention to these things. And this has to do with generalizability. So this is my last sort of like slide. And I just wanted to end up by saying, well, causality is actually hard, but I don't want us to stop doing it. I want us to start trying harder, especially in topics like health, because we must remember, to quote one of my mentors, Nick Jewell, that every data point is actually a human story, and I think we should actually sort of respect the people that we're analyzing and sort of give our best effort, right? So this was my last slide, and over to you, Libby.
Thank you, Carla, for those informative slides and that provocation, I suppose I should say as well. Our next speaker is Rosemary Kerr. She is a PhD candidate at MILA, the Montreal Institute of Learning Algorithms, where she researches causal learning and model-based reinforcement learning, and is, I think, answering or trying to answer some of those questions that Carla raised. Over to you, Rosemary.
Hi, thanks. Hi, I'm Rosemary. I'll be giving a talk today on causality and deep learning. I'm a PhD student at MILA. Where I mostly work on deep learning and causal learning and some credit assignment and so on and so forth. So I'll start off by just giving a really quick brief on what is machine learning. So deep learning, it's a machine learning algorithm. Essentially, it's one way to do machine learning. And machine learning is basically a discipline where we want to learn rules or patterns or algorithms to do a certain task. So imagine that if you have an autonomous driving car, you want the car to drive from point A to point B. You don't want to set out all the possible rules that the car has to follow. You want the car to be able to learn traffic rules, to watch out for pedestrians, to watch out for other cars, to follow, to be able to get from point A to point B. And this is opposed to, for example, things like accounting, where if you're given a task, you're given the context, you're given the person, you know exactly what you have to do. You don't have to learn the rules, you just have to follow the rules. And this is similar to arithmetics and many other disciplines. And what are the ways that you can learn those rules? So there are essentially like two main ways that you can learn it. So you can either use some type of a heuristic, or you can learn it from data. So what I mean by using heuristics are, okay, so those are two images from ImageNet. And imagine you have to do image recognition. So I give you those images and you have to tell me, your model has to tell me what is in the image. So for example, on the right-hand side, we have a car, on the left-hand side, we have a bottle. If I was to give the model a heuristic, I can say, well, if I see something that's like a rectangular shape, like a box-looking shape, and has some wheels, has a window, it's likely that it's a car. And if I see a cylinder with, a cap, something on the top, it's likely that this is a bottle. So this is an example of giving heuristics to your model. Another example is I can just give those image. I can give those image to your model, and I don't tell your model exactly how to recognize what is in the image, but I just tell the model that, okay, so the first image is a bottle and the second image is a car, and the model will have to learn from data what makes it a car and what makes it a bottle. And recently, there's been a lot of talks about, in the past few years, there's been a lot of talks about big data. So big data just means we have a lot of data, at least a lot more data than we used to have. How does this impact machine learning? So when we have a lot of data, learning actually becomes more effective. So learning from data becomes more effective. And learning, defining the heuristics it actually becomes more difficult. So I'll give a simple example. So these are still images from ImageNet. So it's a very popular computer vision data set. So they are all categorized into like different categories, and these are images of dogs. So if I was asking someone to come up with heuristics for a dog, you'll probably think of, a furry animal that walks on 4 legs, that has a tail and an ear. And so this is great, and that fits the criteria of the first 2 images that we see on the left. But then you might see an image on the right, which is, a dog wearing a hat, but you haven't seen the hat before. You haven't defined the heuristic for a hat. Then the model wouldn't know what to do with it. The model would say, I don't know what it is. So if you were, so this is an example of, if you were to hand define a heuristic for every possibility, and when the data grows, when you have a lot of data, this becomes exponentially more difficult. It's actually a lot more efficient if I just give all of these images to the model and ask the model to learn what makes a dog a dog. And I will say all of these are dogs, and the model will just hopefully naturally learn what makes a dog a dog. So this all sounds great, right? So this all sounds great. What could go wrong? So what can go wrong is that we don't have infinite data in infinite time and infinite compute power. So it's true that we have a lot more data than we used to have, but we still have limited data. So what does this mean? This means that the model that we've trained our model on, which is training data, it's not necessarily the model we've tested the model on, which is test data. So imagine if you train up a robot with some data, and now you release the robot in the real world. The robot will see different data than the ones that you presented it. And we want the model to basically generalize to test data as well as training data. And this is not a trivial task. So this is an example here of why this is not trivial, which we'll also get back to later on. So if you see, this is essentially another image recognition a task. So I want to recognize if the person is playing a musical instrument. On the left-hand side, that's fine. I have a person. Their arms are kind of in like the right angle, and they have some kind of object in front of them, and the model recognizes the person as playing instrument. And then the model look at the picture on the far right and says, okay, well, the person's arm is sort of in the same angle as the other 2 pictures, and he has some kind of an object in front of him, so he must also be playing instruments. But any human who's seeing this will know that this is wrong. The person is not playing instrument, they're fixing a bike. So what went wrong? So what went wrong is the model didn't learn to, the model mixed up correlation with causation. So what do I mean by correlation? So correlation are things that happens together but does not cause each other. I'll give a quick example of what it actually means and what other things does it entail in machine learning. So for example, you log on to Amazon, right? So you bought a laptop, and then Amazon recommended you and says, well, why don't you buy a laptop bag with your laptop? And this is great. I've spent like $2,000 on a laptop. I can spend $30 or $50 on a laptop bag. So when Amazon looks at this data, they see, okay, well, laptop also almost always goes with laptop bag. This is great. But now what if you also logged on to Amazon and you bought a laptop bag, and if Amazon recommended a laptop to you, you probably won't buy the laptop. That's because your laptop, the act of you buying a laptop bag is mostly caused by you buying a laptop, not the other way around. So correlation means that buying a laptop and buying a laptop bag usually happens together. But causation means you also have to define the arrow that goes one way or another. So if 2 things happen together, there are basically 3 possibilities. It's either buying a laptop causes you to buy the bag, or you buying the bag causes you to buy the laptop, or there's another variable X, which we're not observing, that's causing you to buy the laptop and buying the laptop bag. So basically, causal discovery means we have to figure out the graph, the underlying graph, and which way the arrow goes and what the relationships are. So these essentially causal models, and Carla has already defined it in her talk as well. So what does a causal model allow you to do? So a causal model allows you to answer interventional questions and counterfactual questions. So what do they mean? What do I mean by that? So as you can see, we have like a very simple causal model on the right hand side. If I was to perform an intervention, that means if I have a little hammer that I can set a certain variable in the environment to a certain value, then I can know how does it affect my other variables in the environment. And in the case of a laptop and a laptop bag, I can say, well, if I suddenly I can raise the purchase quantity of laptops. I ask a lot of people to buy laptops. Would it affect people buying laptop bags? And vice versa. If I ask a lot of people to buy laptop bags, would it affect people who are buying laptops? And what does it actually? What does this actually entail in machine learning in terms of generalization? So we talked about what are causal models, and we said, this is important for generalization. This is actually very important for many things. So for example, if you have a reinforcement learning task, so if you have an agent that's playing in an environment that's playing in multiple environments. So for example, the little grid world that we're seeing on the left. So each one of these rooms can be a little small environment. Any humans who look at it could say, well, the rooms have some similarities, but they're not exactly the same. So some rooms have keys, some rooms have blocks, some rooms have both keys and blocks, and some rooms have, just one of these, and some rooms have just blocks. And yeah, so basically any human who's seen, let's say, any two of these rooms should be able to generalize, should be able to learn to play in all of these other rooms. So we want our machine learning models to do something similar. So we want our machine learning models to be able to generalize to compositional and a diverse sort of compositional environments. So in order to do that, one of the best ways we can do this is to learn a causal model. So why would a causal model allow us to generalize? A causal model is basically the simplest possible representation of your data distribution, and they're also robust. So that means if I have a change of environment like the ones we've seen earlier, a causal model can represent those changes with the most sparse set of changes in my graph, in my model. So basically, it's saying if I had a causal model that I can just change going from one environment to another environment, I can just change a little bit just change a tiny thing in my model, and then I should be able to change from one environment to another. And this means that the changes are localized, the changes are sparse. That means that my models can adapt faster, and my models are probably more robust and transferable. So this kind of leads us to talk about invariances. So invariances and causality are not necessarily the same thing. So causal models implies that if you have a causal model, that implies that your model is invariant. But if you have an invariant model, it doesn't necessarily imply that you have a causal model. So under certain conditions, and also under certain conditions, we've basically found. So this is some of our recent work as well with Joshua and also our co-authors, and we recently found. So basically, if you are invariant, this is a known thing that if you want to be invariant to interventions, then you'll find a causal model. But you can also use a neural network that learns this invariance, that actually learns a really good causal model, because neural networks can model nonlinear relationships really well, and they can learn. They have really good. They have really powerful representation learning power. So we talked about most of the recent work, and I'll now move on to talk about what are the underlying challenges in applying causal learning to deep learning. So as Kara has talked about, in traditional causal learning, most of the time you assume that the variables are given. So if you have medical data, if you have biology data, if you're trying to model things like protein structures, and if you have medical data and you want to know the person smoking, does it cause lung cancer, all of the important variables are given. Variables like smoking and lung cancer, they're all given. But this is not necessarily true, and we can't take that for granted for many models that we use for deep learning. For example, if you have a robot acting in the real world, I can't possibly label every single variable, interesting variable that the robot will see. So the robot will have to go into the real world and will have to basically learn what are the interesting variables by itself. And this is not trivial. So this requires kind of your model to learn. There are two major challenges. So it requires your model to be able to extract what are the interesting variables, and then learn a causal model that models the relationships of those variables on top of it. So here's a really simple example of a physics environment where you have like heavier light objects. Darker objects are heavier, lighter objects are lighter. That heavier objects can push lighter objects, but not the other way around. So if you look at even this very, very extremely simple environment, your causal, essentially what your model has to do is your model has to extract meaningful objects from it. So these are those like little triangles and circles from it. And then to be able to learn this causal relationship, which is demonstrated by this like a little acyclic tunament there, that heavier objects can push lighter objects and not the other way around. But actually learning this, learning this is actually affected by many factors in the real world. And we summarize them to mostly like 3 factors. So one is your physical nature of the environment. So the physics of the environment, whether or not objects move together, gravity, friction, and all of this. And this is pretty natural and people can think about it. So things that defines object and events. And other things like what the agent can see and control. So for example, if you have a colorblind agent going to the real world, even if the agent, even if color is an important variable in your causal graph, but if your agent can't observe color, there's no way the agent could model that. So then this affects you learning a causal graph. And it also matters what the task is. So things like, if I know how to drive a car, I don't necessarily know how to fix a car, but the mechanic would know very well the underlying causal mechanisms of mechanics of a car and should be able to fix a car. So what kind of causal models I learn roughly depends on those 3 different categories, 3 different categories of things. And I think this is something that people have started to look at, and it's a really interesting research direction for the future. And thanks. I think that mostly wraps up my talk. And thanks.
Brilliant. Thank you very much, Rosemary. That was great. I'm going to ask Carla to join us back on screen again. And so I need to get this out of the way so that we can get on to more interesting questions. You both agreed in your talks that correlation does not equal causation. And yet I know that there is some controversy, there's some disagreement between the 2 communities, statistical and machine learning, about causality and machine learning. Can you describe what that is?
Right. So I guess in a perhaps gross oversimplification, I wonder how Rosemary is, for example, able to learn the causal structure from the data without somehow equating this correlation to causation, right? So in my world, mostly, if I observe a correlation, I have to bring external knowledge to be able to sort of say, okay, so either the laptop cost me to buy a bag as opposed to the bag cost me to buy a laptop. So without this external knowledge, I wonder how would Rosemary's deep learning methods learn what was the arrow direction, right? So
you fundamentally are uncertain whether you can learn causal structure from data.
Just from the data. So either I bring data from elsewhere or I bring knowledge from elsewhere. But
I think Rosemary can answer this.
Thanks. That's a good question. So yeah, so that's a good question. So I guess like there are 2 things with it. There's the part of you are given the right variables or you're not given the right variables. And if you are given the right variables, so I think there's also a difference in thinking from, I think, like most of the statistical causal learning point of view and like the deep learning point of view. So I think in causal learning, from like the more classic causal learning point of view, a lot of causal learning was to help with scientists to answer questions. So for example, like to understand medical data and things like that. So their interventions are expensive. So you don't want to, and also you can't just perform any random interventions on any random person. Whereas in deep learning, a lot of the applications in things like robots and agents acting in the real, acting in like a simulated environment, or a robot acting in the real world, but there is actually less price that the agent has to pay for doing an intervention. So let's assume if the agent knows what the important variables are, and if they want to find out which direction, like for example, if it's a laptop that's causing you to buy the bag and or vice versa, you can actually intervene. You can ask the agent to intervene in the environment, and then you'll be able to see what the results are. And in the cases of where the variables are unknown, so it's true that this is a very difficult problem. I think so there's been basically thoughts. So there's been like some recent work in wanting to work in this direction. It's not an easy direction. So you have to, so I agree this is not easy because learning the encoder, learning the variables and learning the graph on top of it, they kind of go hand in hand with each other, and they're not independent. But you can use, like, for example, humans have very strong priors, and I think Josh Tenenbaum talks about it in like some of his papers, like the theory of causality and things like that. So you can use like human priors, like this. Humans want a simpler model to explain the world. So he has this like famous experiment where if you turn on like different switches to the light and you ask them, does one of the switches turn on the light, but you haven't actually observed that switch, but you will mostly answer no because the other switch turns on the light, just because humans have certain type of like priors to say that. So a way of utilizing those type of priors in the model could help the model to learn a causal model. Of course, I guess there's no guarantee that the model can learn the right variable and the right causal model at the same time. But we don't have a lot of choice if we can't possibly label everything for our robots. So these are kind of like surrogate laws and surrogate targets that can allow the model to learn it to some extent.
Does there need to be a guarantee? I mean, both of you talked about the reason that you're working on causality is for its importance for model robustness and generalizability. If Rosemary's models generalize well, isn't that empirical evidence enough?
I suppose, yeah, I would say probably yes. But for example, this model that was sort of training one hospital data to sort of then use it in another hospital for deciding who to admit to the ICU. And unless you look deeply as to why, so the reason why they discovered this problem was because the prediction that asthmatics would survive better was a bit counterintuitive. So they used external knowledge to think, oh, hang on a minute, something went wrong with this model. And I think if we hadn't had that, hang on a minute, this goes wrong, maybe they would have just said, okay, so don't admit any asthmatics to the ICU, and perhaps there would have been a high cost. So I understand when Rosemary says, well, for my robot, it's not so dangerous. It can make a few mistakes. Whereas, for the humans, we shouldn't be able to live with those mistakes, right? We want to make sure that our models are very robust before we deploy them. So this is why, in a way, maybe we should be less ambitious, but more careful. Wherever causal predictions we're going to do, we should understand why we're making them, right? When we're going to use them for life, so to speak, life and death decisions, right?
Yeah, I agree with, I actually agree with that. So I think it really depends on what the risks are. And even for like deep learning models, I fully agree that we should take on any prior knowledge that we already have. We actually tried this for our paper to take on, like, let's say if you are given like a partial graph that what part like the graph is, and you have to learn the other parts of the graph. The model actually learns way faster and everything. So
in a sense, we're not learning from data alone. There's causal structure in some sense included in the model as priors or structure.
Yeah.
So that partly answers the question as well, doesn't it?
Yeah. So maybe we just maybe the traditional sort of statistical causal inference would go by stages, right? And maybe we learn the structure from past data, and once we feel that we know quite well, quite robust, because we've conducted lots of different studies and they seem to suggest that the arrow goes in this direction, then we take it as a strong prior that my causal diagram is this way, right? Whereas I think Rosemary has this luxury of being able to run many worlds in one go, right? And learn what are the robust structures of causality in applied topics like physics or medicine. We only have the real world, so we have to run lots of experiments sequentially to sort of learn this, right? So maybe saying the same thing, and it's just a matter of how we aggregate the evidence.
Yeah, exactly. And also, sorry, I'll just add one point also that I think evaluation for a deep learning model is not necessarily so trivial either. So a lot of deep learning models, so not a lot, but some of the deep learning models that models causality don't necessarily learn a structured graph. So they will have like an unstructured representation that basically can predict interventional outcomes. In this case, it's actually hard to evaluate the model because in order to evaluate it, you have to evaluate it on all possible interventions. And for like agent playing a game, for example, you have to set the agent in all possible state that can be in the game, and and basically evaluate all possible actions. So that's just very expensive. So that's actually a good open question about like how to evaluate these type of models.
When I opened this session, I talked about the hard open problems I was quoting in AI and machine learning being to do with causality. Aside from generalization robustness, are there other benefits to incorporating causality into machine learning, and I guess vice versa as well?
Yeah, so I think there is. So I don't know whether you consider sort of like fairness and biases in the data part of generalization. So certain school of thought would say that. So there's been a lot of debate, for example, of equality of opportunities now with, say, Black Lives Matter, and we know that a lot of our training data is perhaps too based on the the experiences of maybe the non-ethnic minorities. And one worry is that perhaps what we're learning is kind of like biasing against the ethnic minorities, right? So if we were to be able to learn or sort of impose this causal structure, we can try to redress these problems and perhaps sort of like break that arrow of selection bias, if you see what I mean. We know that our data has that bias, and we can sort of like redress it using causal tools. So I think it is important to be aware of the way the data was selected and how we can avoid these biases in other settings.
Yeah, and I agree, and also like I think for example like really simple things like recommendations, like the example of like buying the laptop or the bag. So I think things like that is important to understand what is causing what. In some
it helps with interpretability.
Yes, and with some reinforcement learning as well, and yeah.
And Carla, I am quoting from one of your papers here. We believe paradoxically that machine learning methods that are often criticized for their black box nature may increase the transparency of applied research. Would you care to expand on that?
Yes, so in statistics, again, sort of traditionally, you would be asked to define your analysis plan from the beginning before you see your data. And then it's kind of set in stone to prevent you from sort of cherry picking and sort of like, digging around for results. But paradoxically, it kind of, you then at the same time try to get the best fitting model. So there is a lot of, I'm going to add quadratic terms and I'm going to add interactions, because the model that you set at the beginning is probably not the best fitting model. And I think you end up sort of digging around. Whereas if we were to specify an algorithm that is sufficiently data adaptive, I think it can be pre-specified and flexible at the same time. So I'm trying to sort of like break a little bit the barriers to adoption of more modern methods. Many of my colleagues would think it's like searching around for results, but I think if you do it properly, it doesn't have to be that way. It's about helping finding better solutions. Huh?
Yeah. Thank you. I have one more question to ask, and it's about what is the next research question that you are trying to answer?
Ooh. So,
Rosemary, are you ready to go?
Sure. I think mostly like what I talked about at the end of my talk. We have we're actively working on that. So basically, how to learn what are the essential so we are identifying what are the essential ingredients for applying causality in deep learning, and what affects learning this basically variables and the causal models at the same time. So that's one thing we're looking at. Also, like I think releasing data sets that in environments that allows you to work on that. That's also really important because a lot of the data it's basically it was like pre-deep learning data. So you know there's like 1,000 examples, and you can't really train a deep learning model on that. So these are kind of like important questions. Well, these are kind of questions that we're looking at next.
Thank you. Carla?
So I'm interested in looking at sort of what we call dynamic treatment regimes, and sort of like in time. So what are the sequences of treatments that we should give at different time points of the patient's journey through health, and what is the optimal time to add the treatment so that you maximize this benefit, right? And personalize it as much as possible to your own past. So, because I think there is a lot of data out there, and if we get this structure right, with the causal structure right, I think we can do much better than we currently do.
Perfect. Thank you so much, both of you. This has been an absolutely fascinating discussion for me, and I've learned a lot. I hope that the audience has too. I should mention that there is the opportunity to join the Q&A session in about 10 minutes time. I hope many of you will do so. And I'd like to thank Rosemary and Carla for their brilliant presentations and participation in this discussion. Thank you.
Thank you.
Thank you very much, ladies. That was an absolutely brilliant discussion. Again, so much depth on this stage. One of the things that I've just been enjoying so much watching the cutting edge stage is how deep we're getting into some of these topics. And of course, it being the cutting edge stage, you would expect that, but it's wonderful to see it happen in real time here at CogX. So thank you for that. As Libby said, please do go join the Q&A. It's going to be starting on the hour, go for about half an hour, depending on how many questions you guys have already submitted. Of course, if you haven't already submitted your questions and you would like to join that session, submit more, or even just go and watch and see what everyone else is asking. You're very, very welcome. Next on this stage, in the cutting edge stage, is a talk on scaling voice technology. That's going to be starting here at 5 o'clock London time. Depending where you are in the world, it might be a slightly different time, but please do come and join us for that. That looks to be another brilliant session here on Cutting Edge. And of course, in the meantime, if you're not going to the Q&A, go and check out some of the other talks. The expo's there for everyone to go and see what's being exhibited, and of course the networking rooms too, so that you can hopefully meet some fellow attendees of CogX. Until 5 o'clock, please enjoy yourself, and I'll see you then. Thanks very much.
Want access to more CogX videos? Subscribe now for free at cogx.co.